Extra question 4. A study considered the number of TVs owned by a household. In the sample taken, it was found that households owned up to 4 TVs. The probability that a household had just 1 TV was 0.1. The probability that a household had 2 TVs was 0.2. The probability that a household had 3 was 0.4. And the probability that they had 4 was 0.1. Now, even before looking at the actual questions that go with this scenario, I'm already thinking, okay, we've got a situation with a range of outcomes. We've got a certain number of TVs up to a maximum of 4. We've then got the corresponding probabilities. Now, anytime you're thinking about outcomes and corresponding probabilities, you should be thinking about probability distributions. Of course, when it comes to probability distributions, we also have to think about whether we're dealing with discrete or continuous. When we're talking about a certain number of TVs, well, we can't have half a television, and so there is a finite list of how many TVs that could be owned, and in this case, it's up to 4. So this is a probability distribution scenario, but it is specifically a discrete probability distribution scenario. And if there was any doubt, when we look at part A, it says describe the probability distribution of TVs owned. Now, to construct a probability distribution, we've got to have our random variable, and then we've got to have the corresponding probability. Now here, our random variable is the number of TVs owned. How many TVs could be owned? Well, up to 4. We couldn't have a negative number of TVs. So what would be our starting value? The least number of TVs would be 0. The household could have none, and it could have up to 4. That's what we've found in our data. So list those outcomes, 0 through to 4 in this case. We have a discrete random variable. We then need to show the corresponding probabilities, and we can read through the information to find those. Now we've got the probabilities for 1 TV, 2 TVs, 3 TVs, and 4 TVs. Fill those in, 0.1, 0.2, 0.4, and 0.1 respectively. We are not told the probability of having 0 TVs, but we can work that out because we know that all of the probabilities must add up to 1. If we've got 4 of the 5 probabilities, we can simply add up the ones we've got, subtract that from 1, and that leaves us with the probability of no TV. And in this case, that is 0.2. Always do a double check, run through the list of probabilities, make sure that they do indeed add up to 1, and in this case they do. That must be the case for a valid probability distribution, and so we have our probability distribution of TVs owned. Part B wants us to look at how many TVs we would expect a household to own. As soon as we see that keyword expect, we're talking about probability distributions. We like to find the average of the probability distribution to tell us what we expect to happen. But keep in mind the expected value, which is just our weighted average of the probability distribution, is a measure. It won't necessarily be an actual number of TVs that could be owned. It's a measure. It's giving us an idea of what happens on average. Now, this is a good example of something fairly small that we could calculate the expected value by hand. Now, if you have a look at the formula sheet, you'll see that the expected value of a general discrete probability distribution is just the weighted average. You need to get each outcome and multiply by its corresponding probability, and then you add all of those components together. So it's going to be 0 times 0.2, 1 times 0.1, 2 times 0.2, 3 times 0.4, 4 times 0.1. And all of those components in the brackets you add together, and we come up with an expected number of 2.1. So we have our probability distribution for the TVs owned, and we know that on average we expect a household to own 2.1 TVs.